Okay, okay, so today I want to talk about this thing called the recursion theorem. And that's basically what lets us define things recursively, which is good because that is how we define addition. Okay, so that is, how, and how do we define addition? This is roughly how we should do it. We should define, here's our plan for addition. We just do, what is n plus m plus 1? Well, it's just the definition says, well, you just do n plus m and add 1 to that. So given if you know what n plus m is, then you know what n plus m plus 1 is. In other words, you define, you define it recursively. You define n plus 1 in terms of the smaller numbers n and m. Okay, and the same plan is the plan for multiplication and times m plus 1. Well, that should just be, the definition should just be, well, multiply n times m. And then once you've already defined addition, well, you just add n to that. And same for exponentiation, what is m to the n power, or sorry, what is m to the n plus 1? Well, it's just m to the n times m. Okay. Okay. Another way to write it would be like, we say, you might define it like 0 plus 0 equals 0, 0 plus 1 equals 1, 0 plus 2 equals 2, and then you define what is 1 plus all the numbers. You go like 1 plus 0 equals 1, 1 plus 1 equals 2, 1 plus 2 equals 3, and you just keep on defining it like that. Okay, and then I put dots here. Well, that tells you kind of like that tells you enough to know how to define it, but it doesn't tell you that it's well defined. Okay, we want addition to be well defined. Okay. And just in case you don't know, like doing dots, usually it's like good enough, but not right now. Like dots, using these dots, it's enough to show you that you can see what I mean, but it's not enough to show something's well defined. Okay. So that's our plan. We want to be able to define addition and multiplication. We also want to do things like we want to define n factorial, we want to define like, what is n plus 1 factorial? Well, it's just n factorial times n plus 1. Okay, so the definition of n factorial is also a recursive definition. We also want to be able to define, we just want to do things recursively. We also want to define like the Fibonacci sequence if we want to, like f0 equals 0, f1 equals 1, and fn is just fn minus 1 plus fn minus 2 for all n greater than or equal to 2. That is the definition you might usually see. It certainly tells you how to compute like F100, well, you compute F100 by computing F99 and F98, which you compute in terms of F98 and F97 and so on. But knowing how to compute something is not the same as proving that it's well defined for all natural numbers. Okay, so we want to kind of solve the problem of, like, are these things well defined, or is there kind of like this problem with the dots, I guess? Okay. And also I wanted to do maybe questions like question 2 and maybe question 6 from the assignment, just as an example. Or maybe like some induction question if you want. Okay. So let's start with question 2, just as an example, I guess as a warm-up, if you want. Okay, let me write down what the question says. Prove for all natural numbers n, okay, okay, so we want to prove for all natural numbers that the natural number n is exactly the set of all natural numbers less than n. Okay, now just it seems to be true, you know, if you look at the first few natural numbers, the natural number 0 is just the empty set, and there are no numbers less than 0, no natural numbers less than 0. So this is the empty set and 0 is the empty set, they're equal. Okay. 1 is just the empty set union, the singleton in the empty set, which is just the singleton of the empty set, which is just the set containing the number 0 only, right? And of course, 0 is the only number less than 1, and it's okay, so this set, for when n equals 1, this set is exactly equal to this, right? So it seems to be true at least for 0 and 1, and we want to prove that it's actually just is true, that's true for all natural numbers. Luckily we have you know, we can maybe do it by induction, you know, proof. So let's just let P of n just be the statement that n equals the set of all natural numbers such that m is less than n. Okay. And then I guess we proceed to prove P of n for all n by induction. I'm sorry, I see someone wrote in the chat. Oh, sorry about that. Okay. Thank you for telling me about the people waiting to be let in. I don't know why my thing is not making noises right now to tell me that. Okay. Okay, so we want to prove this is true by induction. First of all, for P of 0, 0 is just defined to be the empty set. And also, if you look at all the integers, or sorry, all the natural numbers less than 0, that is also the empty set. And the reason is because m less than 0, the definition says that m has to be in the empty set. Well, there's nothing in the empty set, so there's nothing in this set. There's nothing in this set. These are the same. Okay, so therefore 0 is the same as all the natural numbers which are less than 0. In other words, both sets are the empty set. Okay. So P of 0. Okay. Now we could keep going. So now we want to assume P of n and prove P of n plus 1. Okay, so if you want, maybe I should say that this is the base case. It was right here. Just so that we can organize our solution, into base case, induction hypothesis, induction step, conclusion, that can help. Okay, so we did the base case. I hope there we go. Okay, what about the induction hypothesis? Assume P of n, which means assume that n is the set of all natural numbers that are less than n. And our induction step is to show, we have to show P of n plus 1. We have to show that n plus 1 is the set of all natural numbers which are less than n plus 1. Okay. And we have some things we've already shown. Like, for example, we've shown, we could just write them on the side, but we've already shown, like, for example, we've shown that m is less than n plus 1 if and only if either m is less than n or m equals n. Okay, so we want to show these two sets are equal. We need to show like one is contained in the second is contained in the first, and the first is contained in the second. Okay. Well, first of all, let m be an element of n plus 1. Okay. If m was a natural number, okay, so let's put down some thinking. Remember that if we knew that m was a natural number, and we know that m is less than n plus 1, and we know that m is less than n plus 1, like this, the definition of m being less than n plus 1 is just this symbol, right? So if we can show that this m is in all the elements of n plus 1 are natural numbers, then we can show that m is in the right-hand side, basically. But remember, n plus 1 is just n union singleton containing n. So either m equals n or m is in n. Okay. Okay, our goal is to show that m is a natural number. Okay. If m equals n, well, our induction hypothesis, I should have said assume p of n for some natural number n. So to make it really clear, we're assuming n is already a natural number. So if m equals n, m is a natural number. And so m is less than n plus 1. M is in n, so m is in the right-hand side. Which is what so we have to show these two things. Okay. The other case is that m is less than n. Well, if m is less than n, then m is an element of the natural number n, which is the set of all. So now I've kind of like used the letter m too many times. So I'll write this as all the natural numbers a, such that a is less than n. Right? Our induction hypothesis says that n consists of all the natural numbers less than n. So if m is in n, oh, sorry, I should have written this like that. In other words, so m is a natural number and m is less than n. And so m is less than n plus 1. Because less than is transitive. As we have shown. Okay. So in either case, so therefore m is in the set of all natural numbers, which are less than n plus 1 in any case. And this shows that n plus 1 is a subset of all the natural numbers, which are less than n plus 1. Okay, but the reverse inclusion is even easier, right? Because this inequality, the definition of this just says m is an element of n plus 1. So oh, I switched. This should have been a. I'm sorry, I'm really messing things up there. Okay, so now let m be an element of the set of all a, such that a is less than n plus 1. Well, then m is less than n plus 1, and the definition of less than just tells us that m is in n plus 1. In other words, this set is automatic, like kind of automatically contained in n plus 1. There's actually not much to say there, you know. This is automatic, this is contained in n plus 1. Now, I've shown that both sides are contained in each other. They are equal, therefore, by what I guess axiom of extension, but we don't need to say that. Okay, so therefore, n plus 1 equals the set of all natural numbers that are less than n plus 1. Okay. And that would be the end. Oh yeah, so that completes the induction step, and then we would say like conclusion by induction. N is the set of all m natural numbers that are less than n. For all n. QED. Okay. So I just wanted to do that example just to remind you, like, if it helps you, you have the 4 the four sections of an induction proof: base case, induction hypothesis, induction step, and conclusion. Okay. Okay. Let us also try, I guess this is a similar question, but let's try also question 6. Question 6 from the assignment, which says, let n be a non-zero natural number. Oh, sorry. And not any of the natural numbers, which I forgot to write in the question. That is, sorry about that. Prove n is equal to k plus 1 for some k. And there's there's a couple different ways to proceed. We could either use induction or the well ordering principle. Just for practice, let's do it by induction. If I had to guess, it seems more natural to do it by the well ordering principle. So I'll maybe leave that as practice for you guys. So the solution, let's try and set it up by induction. Okay. So let's try and do it by induction. So for n, a natural number, there's a couple different things we could do. For all natural numbers greater than 1, let p of n be n equals k plus 1 for some k. Okay. So you see, like, this is an induction where we start from the base case of 1. So our base case is that n equals 1, and 1 is just the same as 0. It's just the definition of 1 is just it's 0 plus 1 is 0 plus 1. Okay, so p of 0 holds. Okay. Induction step. Suppose for some natural number n greater than 1 that n equals k plus 1 for some k. Okay, and now we have to, oh, sorry, that should be induction hypothesis. Sorry. Okay, induction hypothesis is that. Now our induction step. We have to prove that n plus 1 we have to prove p of n plus 1. Okay. But this doesn't even use the induction hypothesis, you know? But n plus 1 is already of the form n plus 1. So p of n plus 1. Okay. So our conclusion p of n holds for all n, for all natural numbers n greater than or equal to 1. There is like one minor point, and that is we need to know that the set of all natural numbers greater than or equal to 1 is equal to the set of non-zero natural numbers. Okay, so now if n is not equal to 0 and n is a natural number, then it must be that 0 is less than n. Because any two natural numbers are comparable. And this implies that 1 has to be less than or equal to n. Because we've already shown last week that n plus 1 less than or equal to n if and only if m is less than n. Okay. I hope that I think we've shown that before. Okay, so the set of all non-zero natural numbers is the same as all the natural numbers bigger than or equal to 1. Okay, and so now we're really done. So every non-zero natural number can be written n equals k plus 1. Okay. So let me now take this 5-minute break. And then when we come back, we'll try and we kind of want to make sure that addition and multiplication and these things are, we want to make sure that they're well defined, that all of the usual properties hold with them. Okay. Okay, so I will see you guys in about 5 minutes. Okay.